Good. Stefan, what do you think? Should we start? Should we get started? Yeah, we should. Okay. Hello and welcome to the second talk of the Rust Linz meetup. We are really enjoying ourselves here at the sun deck of the Grand Garage, and in the pause I already shared a short video, a drone video, which our friend Raphael has shot, and we will share more videos about how it is here in Linz, live being at the meetup. I hope the summer will be long and we will be able to do more in-person meetups here at the sun deck of the Grand Garage. But now let's get into our second talk. Let me quickly introduce myself before I go right into the topic. So let me switch it up here, and now it is like it should be. Okay. I think a good idea is to introduce oneself. Let me quickly introduce myself to you. My name is Stropek. Together with Stefan, I founded the Rust Linz meetup. Personally, I am a passionate software developer. I have been writing code for more than 25 years, and I always say every day where I can write code is a good day. Unfortunately, I can't write code every single day because if you work in IT for a few years, you have some management to do, you have some project management to do, you have to do some sales stuff and so on. But many days are, for my personal life, are coding days, and I really enjoy that for more than 25 years. I'm a Microsoft MVP and regional director. That does not mean that I'm on the payroll of Microsoft, not at all. That means that I do just a lot of work with the community, and if you do that, you are promoted to a most valuable professional or a regional director. That's all. So, to make a long story short, beside my professional work, I do a lot of trainings. I am a part-time teacher. I'm a mentor in the community. I'm chairman of the Coding Club Linz. We run the local Cododojo Linz, which is the programming club for kids here in Linz, and of course the Rust Linz meetup. That's essentially me, and if you would like to get in touch with me, on the right bottom side of the slide you see my digital business card. Just click on the link or type it in, it's not that complicated, and on the right lower bottom you find links to LinkedIn, Twitter, Facebook, my YouTube channel, and so on and so on. So I invite you to get in touch with me. Enough introduction. Let's take a look what we are going to do. We are going to play tic-tac-toe. I said I love writing code, and I learn most when I write code. And one of the traditional things that you build in a new language is a tic-tac-toe game, and today we are going to build tic-tac-toe. Well, it will be more of a code walkthrough because so many things are here, live, here, outdoor, and so on. So I wasn't brave enough to type the code live, so it will be a code walkthrough, and I will show you my points with existing code. And of course, I will over-engineer the tic-tac-toe game a little bit, because then with an over-engineered tic-tac-toe game, you can learn a lot. On the way of building this tic-tac-toe game, we will learn some things about traits. If you want to take a look at my code in detail, I cannot talk about every single line in just an hour. You can use this link that you find here in my slides, and you can click on it, go to GitHub, and take a look at it. By the way, I maybe should quickly share the link of my slides. Let me do that. Let me quickly go to slides.com here and have, where is this one, and let's share this one. This is the link, you see? This is the link, and can I quickly copy that into the chat? I think so. I think I can do that live. And here is the link. It's in the YouTube chat now. So if you would like to follow the slides directly online, you can now take a look at the YouTube chat, and there you find the link to my slides. Good. Without any further ado, I would say let's get going. Thank you, Stefan. Please, go to, yes, next slide. Okay, internet is a little bit slow here, so you don't see this funny GIF here. That's one of my favorite games when I was, too fast. Don't do the spoilers here. Just one. This is has been one of my favorite games when I was a kid. Anybody know this game? Yeah. Prince of Persia is exactly, and you see this one is really the basic stuff. We are just entering the first level. We are opening a first door, and that is a good thing to get started to talk a little bit about traits. Okay? What is a trait? Let me quickly copy this one to show it to you live. This is a very, very simple example, and in order for you to follow along more easily, I will go to the Rust playground. Give me the Rust playground here. Come on. Here it is. And let me copy in these few lines of code that I have here and zoom in a little bit. You know, when I first played with Rust and I read about traits, then I viewed traits from the viewpoint of a C# TypeScript developer kind. Because I write most of my days C# code, TypeScript code, sometimes a little bit of Go code, but to be honest, I viewed it from the viewpoint of a C# developer. And when I found something like this, as you can see it here, pop, trait, computer, get answer, self, whatever that self is, self sounds like this, and this arrow with U8 means we are returning probably a byte, something like this. This looks very much like an interface. I know that. In C#, I would build a struct or a class. I would create an interface, something like this. This could be a struct. You could ask yourself, why a struct without members? Yes, that's possible. That's definitely possible in Rust. That is called a unit struct. And then you can implement, as you can see it here, you can implement a trait for a certain struct. It looks a little bit different than in TypeScript or in C#. It looks pretty similar, kind of with Go, but it feels like an interface. It sounds like an interface. It smells like an interface. I think I understood that. That is fine. And as you can see it here, I can instantiate deep thought, and I can ask deep thought for the ultimate answer, and probably if I run this, I will get 42, of course. That's a very simple getting started. That was my first introduction to traits. But when I got more interested in the details, let me try if I can zoom in a little bit, I was asking myself, okay, what happens behind the scenes? And if we take a look at the generated assembler code, and I have copied it out here, I used the Rust playground to generate the assembler code. What I essentially saw is that this interface was nearly gone. It's not visible. Well, it is kind of visible a little bit, only in the names of the generated jump labels here, but essentially it is gone. If we call this method getAnswer, which is a method from a trait, then we essentially get a call assembler statement, directly a call assembler statement with the static dispatch of this method. Really, really simple. So I think this is what many Rust developers means when they say zero trust abstractions, zero cost abstractions. I'm very sorry. They are trusted. Okay, not a good phrase here. This is what you can call a zero-cost abstraction. You can build interfaces and you don't pay for them at runtime. That's a very good news. Okay, now let's go into our tic-tac-toe game and take a look at basics applied to the tic-tac-toe game, and then we work our way through to more complicated stuff, because this talk is called Traits Are Not Your Grandparents' Interfaces, so obviously there has to be more about these traits. Let's take a look at one of my first things that I implemented here. Let me quickly look for the code that I would like to show you. Where is it? Where is it? I'm going to find it, and it's here. Let me zoom in a little bit so you see it pretty good, close. Here you see a trait. And in this case, for demo purposes, I created a structure which is called board content. It will hold the data for my tic-tac-toe game, okay? It contains essentially a 3x3, so 9 elements of size U8 array. So 9 bytes for 3x3 elements for our tic-tac-toe game. And in this case, I wanted to build an abstraction which I called toCompactString, which does nothing else than taking all these 9 elements and turning them into a string. Very, very obvious code. Even if you have not written a lot of Rust before, you will probably be able to understand this code from the context. There is a lot going on here with traits, but we will discover that a little bit later. For now, you see the board content, which is my struct. Here you see the struct, and you see the toCompact string, which is a trait, and I implement this trait for my board content. Okay? That should be pretty obvious. Any questions to this code? Maybe those of you who have not written a lot of Rust code, I know there are some people here in the audience who have not written Rust code. Some of the beautiful things, do you see the missing return statement? Yes, I don't need a return statement. You see, I just write result without the semicolon at the end, and that's the return. You know what? Since I mix Rust and C#, I think people think I'm stupid whenever I give C# talks, because I always forget the return statement. I call myself a C# trainer, and I don't know how to write a return statement. So if you see that, if you see me doing that on stage, now you know why I do that. Because maybe in the morning I wrote Rust, in the afternoon I write C#, and I always mix it up. So this is Rust, this is interface, this is traits, and this is the first step. Let's go back to the slides, and let's take a look at my second node. Yes. Let's take a look at a little bit more advanced example. Let's fold that one, and let's take a look at this one. Let's make the font a little bit larger so everybody can see it properly. Here you see this one, a square content. It's an enum. Many of you know enums from many different languages, and Rust has enums too. This is a so-called fieldless enum. That means we don't have any additional data, because in Rust we could give additional fields to certain elements of the enum if we want to. So we could say, well, in the case of an X, I want to have additional data like A8 or a whole struct or whatever. We could add additional data, but I'm not doing that. The first thing that you have to see and recognize here, and that is pretty awesome, see that one? We can implement traits. In this case, this is a system trait, the default trait. That allows Rust to understand what the default value of a type is. I didn't define this trait. This trait is system defined, but I can define traits on enums. That's pretty awesome. In many other languages, you can't do that. Additionally, you might recognize that up here I have this strange thing, hash derive, with debug and copy and clone and partial equal and equal. Guess what? All these things, debug, copy, clone, and so on, are traits. And what you see here in line 4 is the so-called auto-implementing. We can just ask Rust to auto-implement all these interfaces for us. This is a macro, so Rust comes with macros, and these macros can auto-implement traits for us if they are pretty simple. For instance, there is a trait here, copy, which just says, I can copy this data type by copying the underlying bits. This can be auto-generated. There is no reason why I have to write code for that. And this is the derive macro that you see here. By the way, if you want to know what's going on behind the scenes, you can always copy this stuff, go back to our good friend, the Rust playground, paste it in, and then somewhere, I think it is here, yes, expand macros, takes a second, and here we are. See, this is the code that is generated. No, I will not walk you through this code. You can do that experiment on your own, but that's essentially what's going on behind the scenes. Auto-generating traits for your data types whenever they are pretty simple and when they can be auto-generated. That's going on in the first few lines of code here. So you see, a little bit more than just interfaces, isn't it? Let's go further. The next thing here is another system trait that I implement here. You see, square content is again our enum, and this time I'm implementing the from trait. From is typecasting. If we want to have typecasting, we implement the from trait. So in this case, I'm saying I want to be able to generate a square content from an unsigned byte, from 8 bits. And then I use the match statement of Rust in order to turn the values of the unsigned 8 into square content fields. If the value is not available, then we just panic. Oh my God, I cannot convert that one. Okay? The beautiful thing here is that there is a second trait, which is called into. It works exactly the other way around. So what you can say, you could say implement into for U8 for an 8-bit unsigned 8-bit unsigned byte to turn it into a square content. So we have from in one direction and into in the other direction. So which one should you implement? And now comes the beautiful thing, something again new for those of you who haven't looked so deeply into Rust. You get it for free. If you implement from, you get into in the other direction automatically without writing a single line of code. If you are not an experienced Rust developer, you can now ask yourself, how could that be? How is that implemented? Is that magic built into the Rust compiler? No, it isn't. I will show you the source code in the Rust library in a few minutes, where you will see how this magic is done, how this works. And guess what? The magic is traits. Again, traits. Okay, here you see, yeah, question.
Does it work only if you implement from? If you implement into, will it?
Oh, very good question. I will repeat this question. Could I implement into and get from for free? Yes, you would do that. But it is recommended that you always implement from and not into. That's a kind of that's a kind of convention, if you want. Stefan.
Into is implemented in the standard library.
Yes, into is also.
For all,
yeah.
Everything that implements from gets an into.
Exactly. That is what I meant with you get it for free.
Yeah, I
yes.
don't think it's vice versa. I haven't seen the from trait implemented.
I'm pretty sure.
Okay.
I'm pretty sure. I'm not 100% sure, but I think I have to check it. It's a good thing. I have to check it. But if you implement from what I said, you get definitely into. Okay, and just implement from, that's the convention. Thank you, Stefan, for pointing that out. If I'm wrong, I'm very sorry for that. I always implement from, so maybe I forgot something. You see, I wrote some type conversions, and let me quickly go down here. For those of you who have not written so many lines of Rust code, these are unit tests. You see, line 63, 64, these are unit tests for the code that you have seen above. And now we can take a look at how these traits are applied. You see, for instance, take a look at this line of code here, this one, line 71. Here, I'm saying default. Default is the name of the trait. I can call here the method default, and Rust is smart enough to recognize that on the left-hand side of this assert statement, I have a square content, and it automatically knows that it has to call the default implementation of square content in order to be able to compare both sides of the equation. Understood? Yeah? For the C# developers here in the room, that would be the default keyword in C#. That would essentially do the same. But here, even that functionality is based on traits, the default trait. Here you see the from and the into part. Let me quickly draw a little bit here. Here you see the from code where I convert a 1 byte into the square content. And again, Rust is pretty smart, even with the traits. If I hover over the 1 here, it recognizes automatically that this has to be an U8, because the from trait into the square content is implemented only for U8. So therefore, I don't need to specify that this is a byte value. I could do that, but I don't need to. Let me quickly show you that. Come on, internet, wake up. Hello. There is a short internet glitch here. I hate that when that happens. Yes, my Wi-Fi is suddenly gone. Luckily, we are projecting from a different computer, which still has Wi-Fi. So let me quickly switch to our second Wi-Fi. I hope it will work. We have 3 Wi-Fis here, just to make sure. Okay, so let's see. And it looks good. Here we are again. Very good. We are online again. Stefan, it was a good idea to bring so many Wi-Fis with us. This is what I meant. You see it? Oh, it's a little bit slower here. It's fine. Here you see, this is what I meant. I don't need to add U8. Rust is analyzing the traits automatically, and it finds out that this U8 is not necessary because it understands that the from trait is available for U8 into square content, and it does all the magic automatically. Okay? And here you see that it works vice versa too. 1.into, I get it for free. 1.into calls the from trait, but the from trait is implemented in the other direction, so it works pretty well. Raphael, you have a question? You want to know what happens if I, for instance, say something like I32, something like this. Then we will get an error because, let me hover over it, there you see that there is no from I32 trait, so therefore Rust cannot fulfill this magic.
Is there a from trait between I32 and U8?
No, in Rust, type conversions are always explicit. You don't get implicit type conversion if the compiler cannot be absolutely sure. If it is absolutely sure, then you get it. Otherwise, you have to explicitly write typecasting. Thank you for this question, Raphael. So this is the into part. Next one is string. I did the same for a character, as you can see it here. And just to add a little bit of extra for those people here in the audience who have not written so much Rust code, this is how you would write a unit test which is expected to panic. It has nothing to do with the trait, but I decided to just let it in here so you see it and maybe it's interesting for you. I see some people nodding their heads. I know you are C# guys and TypeScript guys and so on, so you have probably seen a little bit of Rust but not so much, so this is how it looks like. So this was, again, a little bit of basics, and with that I go back to my slide deck. This is the wrong one. This is the right one. Here we are. We saw from, into, default, everything's fine. Now let's go one step further and take a look at the board index class that I created. Not class, of course, a struct, because we are talking about Rust here. What is the board index? The board index is a struct, here you see it, which contains behind the scenes just a usize value. A usize value is just an indexer in an array, and the size depends on the machine's register sizes. In my case, it's a 64-bit machine, so it's a 64-bit value that you see here. That's usize, essentially. And what I want to build is I want to build a secure way of indexing in our 3x3 board. So I want to build an abstraction on top of usize that can only contain valid values between 0 and 8. Nothing else. And then I would like to build an indexer logic in our board where I can specify indexing, a custom indexer with our own type. Okay? So let's take a look at that one. Here you see, this is our board index type. The implementation is not that interesting because we want to focus on traits. Okay? The implementation of board index is not so relevant for traits, so I will quickly go through that and go down, down, down here where we start to see again some of the traits. The first traits are pretty obvious because you already learned about them. I built a type converter from usize to the board index. Okay? Sorry, the other way around. This is what, sorry, I was confused. This time I'm implementing an interface on a standard type, usize, to be able to convert usize, sorry, the board index into usize. Now I have it correctly. Sorry, I was a little bit confused. So I'm telling the system, whenever you have a board index, I'm clicking too much, and it's too slow here, so here we are. Whenever you have a board index and you need to have a usize, you can directly take the inner value of the board index and return it. So this is another takeaway that you can get from this talk. You can easily implement traits on top of system data types. In this case, I'm implementing a trait for usize, a type which I definitely did not implement on my own. I can also add it to a string, which is a Rust string. This is not a string that I invented. I'm allowing here to turn a board index into a string by just formatting it as a number. Nothing special here. The other way around is just calling a method. This method checks whether the value is between 0 and 8. That's fine. And I also do some parsing. How does parsing work? ix is a string. And now suddenly Rust knows that parse has to parse a value and turn it into a board index. How does it know that I invented the logic that a board index is represented by a string combination like A1 or A3 or C2? How can parse know what to do? Now, what is the talk about? Traits. Therefore, it knows it because we have a trait. There is a system trait which is called FromString, and FromString essentially powers parsing. So if you implement the FromString trait for a data type, in this case a static string, I just implemented here for a static string, and then I can write some parsing logic. And here you see, I will not go into the details because this is just Rust, and if you're not familiar with Rust, you can take a look at the code afterwards. The essential thing that I want to tell you here is that this again is a trait, and by implementing this system trait, I get the parse statement for free. It knows that it has to call the FromString trait, in this case the FromString implementation, so to turn everything into a valid board index. Some of you might have a little bit of problems here because you might ask yourself here, what is this result all about? That's essentially a data type in Rust where I can specify that the result can be either self, in this case the board index, so I successfully created a board index from the string, or I create an error type. Result is an enum, and this enum has two possible values, OK and error. OK would be that one, and if I scroll down a little bit, you see this is the happy case, and this is the second one. This is the error case. This is where you have something like this. So this is how the FromString, the FromStr trait works. You just return either the OK happy path or the error, depending whether you could parse the value. And everything is built on top of this trait. Let me quickly take a sip here and wait whether we have some questions. Matthias asks, any reasons why you didn't use rustdoc 3/? Here in this case, it's not really, Matthias, it's not really a documentation for this trait. It's just notes for me to remember what I want to tell you. So Matthias is perfectly right. Rustdoc, the correct way of writing documentation in Rust is with 3/ and not 2/, but these are just my personal notes, not documentation. We have a video, I think, Stefan, in our library where we had a full hour talk about how to create awesome Rust documentation. So if you are now confused by me doing it not right, take a look at this video. This video is awesome. You will really learn a lot in this video. Check out Rust Linz AT, you will find it there. But thank you, Matthias, for pointing that out. Let's scroll down a little bit, and we have a new trait. Of course, traits, the display trait. What is the display trait all about? The display trait is the trait that is used by the print line macro or the format macro. Let me quickly scroll down a little bit and let me take a look. Do I have a unit test for that? Yes, I have a unit test for that. You see, this is the using of the display trait. Whenever you use the print line macro or the format macro to turn a board index into a string, and you use this curly braces open and close thing here, Rust knows that it has to call the display trait in order to turn the board index into a proper string. In our case, A1, B2, C3, something like this. There is another trait which is important in that regards. It's the debug trait. You can auto-implement it, or you can implement it by hand, and this is used whenever you use the : syntax to print the debug output of your value. Okay, that is a different trait. But in this case, we are talking about the display trait. This is another important one that we have in this example. Display trait. Last but not least, we have two interesting ones. Add and sub. Again, two system traits, and these system traits power what? What do you think? Plus and minus. They are powering operator overloading. So you have to implement a trait and in order to be able to use the plus and minus operator. So in this case, I'm implementing add and sub on the board index so that I can add and subtract board indexes from each other. Let me scroll down a little bit and see whether I can find the prop. Yeah, here you have it. You see? Here in this case, I am taking a board index and I'm adding let's hover over it, usize on top of it, and the result will be another board index. And here I can subtract something from my board index in order to reduce my board index, and the result is again another board index. So if you want to have operator overloading in Rust, implement system traits and then you get support for the plus and minus operator out of the box. So you can already see that traits are very, very deep into the ecosystem of Rust. Whenever you write Rust code, you have to deal a lot with traits. Other languages, like C#, a language that I know for more than 20 years, I think, they are doing it completely different. They are having, for instance, static members on types where you can do operator overloading, completely different like Rust does it here. By the way, if you ask yourself, hey Rainer, what is this stuff? This has nothing to do with traits. This is a very interesting crate. It's a kind of library which is called RSTest. RS is not my name, it's not Rainer Stropek. I have not written it, somebody else has written it, and it's essentially data-driven unit testing. You can easily write data-driven tests like this in Rust. It works like a charm. I really like to use it. And I think even those of you who have not written so much lines of code in Rust, you will be able to guess from the context what this stuff is all about. Nice. So let's go back to our slides and let me check. Yeah, I promised you that we will take a look into why we get this into for free if we implement from. And what I did is I looked up the relevant code piece in the Rust library in GitHub. And here you see what the magic does. Take a look at that one. And that is pretty awesome and pretty different to many other languages. Latest here, at that point in time, you should understand that traits are way more than the usual interfaces you might know from other languages. Take a look at this type. This is an implementation of the into trait for any type T, line 45 here, for any type U, where U implements from. So essentially, into is auto-implemented for any type offering from by just calling from in the other direction. So you can implement traits on top of other traits. You don't need a concrete data type. Trait in German means Fähigkeit. So you can derive a trait from another trait. Let me say one German sentence here so that it's very clear for the audience. Eine Fähigkeit auf Basis einer anderen Fähigkeit ableiten. This is what you essentially do here. And by having this line of code here, we get into for free when we implement from. Pretty nice, isn't it? Okay, very good. Back to the slides. Did I forget anything? No. Let's continue. Board content. I showed you that we have a trait there which is called toCompactString. Let me go back to the board content. Here it is. I implemented toCompactString and I implemented it on top of board content. But I asked myself, what can I show you more? How can I show you what we are capable of doing in terms of doing more powerful abstractions? And here I have added a second trait, board iter toCompactString, which is very similar to the toCompactString trait, but this time it's the same signation, you see it? I can I can turn it into a compact string representation, but this time I'm implementing it on top of, you see it here, an iterator over an array. So I'm no longer implementing the trait for a concrete type like the board content struct, but I know that my board content internally has a static sized array, 9 elements. Therefore, it is very simple to implement an iterator. Essentially, the array already implements an iterator. And if I have an iterator, I can abstract my trait, board it to compact string, away from the board content and build it on top of the iterator over the array. And therefore, my trait implementation is now more flexible. It works with any iterator over any 9-element array here. It doesn't need to be my board content. It can be your board content, as long as you can provide a static iterator iterator over an array. You're fine. My implementation will work for you. So this is the application of this building a trait on top of a trait, now not in the standard library, but in my own application. I can make my implementations more flexible. I can make it more widely usable. That's the idea here. It's just a demo, so don't ask for the why is this really a good idea? Is this the best design? Probably not. But I want to showcase some of the features, what you can do with traits. Okay? That's my point here. So let me take a sip of water here and wait for any possible questions. Okay, good. No questions currently, so I think you want to know more. Good. I just opened Pandora's box of the iterators. No, it's not Pandora's box. It's a huge cake, a huge playground. Iterators are awesome in Rust. I come from the world of, I mentioned that before, C#. And in C# we have an awesome functionality which is called link. I love it. Language integrated query. It's so awesome. MapReduce if you are a JavaScript developer. And in Rust it's iterators. On top of iterators you can do all the crazy stuff like mapping and filtering and summing, and all this stuff is built on top of iterators. So let me quickly show you how we can turn our board content into an iterator. That's pretty simple. We can, for instance, implement the trait into iterator for our board content, and then this into iterator trait has something unique, which is again very special for Rust, and I don't know this feature from other interfaces, from other implementations of interfaces in other languages. In this case we have, let me draw a little bit here, we have parameters for traits. So the into iterator trait demands 2 parameters. You have to tell it, okay, what is the type that we will get back item by item. And secondly, you need to specify a structure that you will use as your iterator, because the iterator is represented by a structure, by a data type. If you create an iterator, you are essentially creating an instance of a struct. And you can choose this struct. You can choose which struct you want to use. In this case, I'm just using the existing struct of the underlying array. So I'm using the array into iter, and I'm just asking my internal array for its iterator, and I'm just returning it. And with that, I offer the array iterator on top of my board content. In a second, you will see that we can build completely custom iterators with complete custom iterator types. You will see that in a second. But in this case, I'm just saying I am hiding the implementation from outside, but I'm passing on the existing iterator logic by using the existing array iterator and just returning it here by implementing this into iterate. And when I have that one, I can, for instance, use a loop statement to iterate over my board content. Understood? Okay.
Sounds like Haskell.
Sounds like what?
Haskell.
Sounds like Haskell was the comment. I have no idea because I've never written a single line of Haskell. I believe you. I absolutely believe you. Let me show you what we can do with that if we take that one step further. I have implemented here you see it, a bunch of types in order to be able to show you how you can build a completely different iterator. In my case, I want to implement an iterator which allows me to iterate over the rows of my board. Remember, I don't have a 2-dimensional array. I have a single-dimensional array with just 9 elements in it. And I want to build an iterator, a virtual iterator, which iterates over rows which do not really exist. There is no data structure internally that has rows. So how can I do that? First, I implement a structure which is called row. This is a small data type which holds a reference, a pointer to the underlying board content and the row index, a pointer and an index. You might ask yourself what this funny thing is like. This is a so-called lifetime. It has nothing to do with traits. It is a different topic for a different talk. Just so much you need the lifetime here because Rust needs to understand that the row can never outlive the board content. That it cannot happen that you have a board in your hand and you already destroyed the underlying board content. In C# I could do that. And if I do that and I try to access the underlying content, things would go horribly wrong. In Rust, the compiler is smart. In Rust, the compiler has these lifetime annotations, and with that, it doesn't need a garbage collector, and it can still mathematically prove, that it will never happen that you have a row that outlived the underlying data type. This is what lifetimes are all about. You can use lifetimes in traits, definitely. I will not go into the details here, but I just want you to be able to follow what I show here. So if you ask yourself, what is this? This is a lifetime annotation. I'm binding the lifetimes of these two things together. Now I have a bunch of implementations. That is not that interesting. I will go down here because now it's starting to become very interesting. Now I start to implement the rows iterator. The rows iterator is essentially an iterator which again holds a reference to the board content and the next row. And the interesting part comes here where I implement now the iterator trait, which is the standard iterator trait for my rows iterator. And the only thing that I have to in the background implement is the next method. This is how iterators work in the background. The system will just call next over and over again, and I can write my own custom business logic, and what I have to return is an instance that I will get back from this iterator. So if I run through the rows iterator, I will get one row instance, you saw it before, one after each other. I'm just maintaining a counter here, and I'm adding 1 to the counter whenever I call next. If I'm at the end, I just return none. If you are new to Rust, none is Rust's null. There is no null in Rust. Rust has the option type. And the option means either I have something for you or I have none. There is no possibility for null. Null is not supported, at least in the safe Rust context. And we are not going to talk about this ugly, unsafe stuff, which we are not going to talk about that. That's a completely different talk. So you see, you can easily implement these iterators. Now, what does this give me? Let me quickly jump back to my board content and scroll down to a nice little piece of code which I have. Where do I have it? No, I'm in the wrong file. Here is this nice little code. This is what I was fighting for. See that one? For row in self.rows. Rows returns the iterator that you just saw. And because this is a system trait, my iterator is capable to work with a for loop. So by implementing this iterator trait, the for loop now calls my next method, and every call to the next method returns an instance of the row, and then I did the next interesting stuff. See that one? I'm able to index inside of the row by using this indexer down here. So the square brackets. And that will be the column inside the row. And that will be the next trait that we are going to take a look at. The index trait. But I hope you understood now that this is pretty awesome. And by having this iterator support, I get really strange things. I can, for instance, say, see that one? Hey, give me the nth row inside my board. This is a feature, this is a functionality that I get out of Rust's awesome iterator logic. You could do, give me, skip some elements, or take some elements, or filter some elements, or map some elements. And in this case, I just use the nth operator. This will give me the first, in this case, it starts by 0, so the second row. By just calling my next method 2 times and give me the second row. So by implementing this iterator trait, I open the whole possibility that Rust brings with its iterator library. Okay? And this is a completely custom implemented iterator. Nothing standard iterator stuff. It's completely written from scratch with my rows. Any questions so far? Good? Nice. I promised you indexing. And indexing is here. Let's do it that way. Okay. This one and this one. These are 2 additional traits that I want to talk a little bit about. The index trait enables us to access our data structure with the square bracket syntax. It allows us to build a custom indexer. The first one, you see it here, receives a reference to self, to board content, because this is the data type that I want to be able to index. And because it just says is a reference to self, it's a read-only reference. If I take a look at the IndexMutable down here, this is the second trait I would like to mention. You just write reference mutable self, and that means I can write into self, into my own data structures. And this is a deep immutable. That's not a shallow immutable, but if I have an immutable reference, I cannot manipulate whatever I have and whatever is inside of my own. Again, there is Rust magic with which you can allow certain things, but the default behavior is exactly like that. It's an immutable version of myself, and I cannot manipulate myself. So I can only return, as you can see it here, I can return an element from myself. But if I take a look at the IndexMutable, here I can return a mutable reference to an element of myself. Don't get me wrong, the IndexMutable is kind of interesting. It doesn't do the writing. The IndexMutable trait takes a reference which points to some data structures that I internally use and gives back to the caller a so-called mutable borrowed reference. So the caller gets a reference that the caller can use to write something into this memory. Understood? That is what IndexMutable is all about. And if you ask yourself, oh, Rainer, what can then happen with parallel, what can happen with parallel programming? Do I need to worry about some race conditions and things like that? No, you don't. Because the ownership and borrowing system of Rust protects you from shooting yourself into the knee. Yeah? The ownership borrowing concept is again a very good topic for another day, for another Rust Linz meetup. I'm not going to talk about it, but just trust me and believe me, if you build safe Rust, not unsafe Rust, you don't need to worry about parallel programming and about data races and things like that. These things are gone, they are no longer present. Without the garbage collector and without a heavyweight runtime. That's the awesome thing of Rust. That's the magic of the Rust compiler. Okay, so IndexMutable. Good. Yeah, that is not that interesting. I had some indexer and that's good. And last but not least, before we go into the last few minutes, I think I have, 10 minutes left or so, and then I'm done. Let's take a look at game. Game is another interesting thing. Maybe it's interesting. I'm not sure. I hope it will be interesting for you. What I did here is I had another idea for something that I can show you. Try to concentrate for the last few minutes here. You see, I invented, here you see it, a trait which is called square assessor. It allows me to access a square inside of a tic-tac-toe board. And I implement two different methods, get and set. I think it's pretty obvious what this thing does, right? Pretty clear, not very difficult. For those of you who are quick and who take a close look at my code, you will probably already have recognized something up here. See that one? mock all, auto mock. Does that ring a bell to you? Of course we can use traits for mock objects for unit testing. And I will show you that in a second. This is why I implemented this trait. This trait is mockable. And this nice little crate is something different than a trait. Okay, for those who are new to Rust, the crate is like in C# a NuGet package, or in JavaScript an npm package, or in Java, oh my god, I have no idea from Java. Maven? Did I say something wrong? No, not really, kind of. Let's not talk about Java. NuGet and npm, I'm sure about that. A crate is the same in Rust. And mock all is a crate, a nice crate for mocking. And here I'm telling this mock all crate to auto implement a mock object for my trait, which I can later on use for unit testing. Okay, you will see that in a second. But the second important thing here, you will see that here, is this line. I now implement the square assessor not on top of my board content, because I don't need a board content for that. I implement it on top of any data type that supports indexing via a board index. This was the save index that we built together, and that returns a square content. So if you want to build a data structure with a backing vector for your tic-tac-toe game, feel free to do so. As long as you allow me to index with my board index and you return a square content, I am fine. My game controller will still work on top of it. So again, an application where I implement the trait on top of another trait instead of implementing an interface on a concrete class or structure. Get it? Clear? Awesome. And with that, I can do crazy stuff. Something like, let's take this one. This checks a method which is called isValid. It just checks whether it can never happen that we have two X's and no O's. So a player has set 2 times and the other one has never set. Something like this is discovered with isValid. But in this case, I would like to implement, to test this logic of isValid without having a real board content. I'm using the mock version of my square assessor. You see it here? This struct mock square assessor was not created by me. This is the result of the auto mock macro that you have seen before. It took my trait, my assessor, my square assessor trait, and created the structure which is called mock square assessor, and I can then mock, for instance, the get method and implement some lambda function here, which is called whenever the get method is called. And in this case, I'm just returning x then o then x then o, so this will be a valid board, so I can assert down here that isValid really returns true. That is my unit test. And if we take a look at the second test here, this is the error case. In this case, I make sure that this board is not considered to be valid, because in this case, I'm returning a given value, x or o, 2 times, and all other elements are empty. And that's not allowed, because then x has shot 2 times, or o has shot 2 times, and the other one has never shot, and that is not a valid tic-tac-toe board. The business logic is not the point. The point that I want to make here is really the possibility of implementing traits on traits and of using traits for mocking. You might ask yourself, can I use structs and mock based on structs? Yes, that's also possible. So AutoMock allows you to build mock structs on top of other structs. That's possible, and in some cases you really need that. For instance, I do some work with the Rocket framework, which is a framework for building web APIs in Rust. I really like it. I've done a talk at the Rust Linz meetup about it, and whenever I have to do unit testing with mock objects, for instance, to mock away my database or backend microservices, I need to apply AutoMock on top of structs. Awesome. Good. You have learned a lot, and we are already nearly at the end, but I would like to show you one last thing, one last look behind the scenes. I would give you this magic sword that you just saw here. And I will not show you that in details because I have prepared it here in my slides. Come on, Internet, show me now next slide. Oh, isn't that nice? You can really read it very nicely. No, probably not, so I will zoom in a little bit. I want to show you what's going on behind the scenes when you implement some traits on top of a structure. Let me go up here a little bit, and then it should be readable. Hopefully it will be. Yeah, I think you can read it properly. Is that okay? I think it's okay. Please check that here I have implemented two structs, cat and dog, and I have implemented the trait animal. Now here I have implemented a function which takes an animal, and please recognize the impl keyword here. I essentially say the print sound method should be applicable to any animal. Anyone who implements an animal can call print sound. Now the interesting thing here in this last demo of my talk today is what's happening behind the scenes in assembler language. In assembler language, we get two different copies of our print sound method. The process here is called monomorphization. So it duplicates the necessary functionality in assembler language so that we don't have to pay with a dynamically dispatched indirect function call. We get a static dispatched function call. One version calls the dog, one version calls the cat, and of course, a statically dispatched call is really, really fast. So by calling, you see it down here again, by calling print sound with cat and dog, you see it on the left lower corner here, I do monomorphization and duplicate the code. So I get better performance, but I get a little bit larger code base. This is what's happening when you use this impl keyword. You cannot use impl always. In some cases, it's not possible. And then you need the second keyword, and that will be really the last keyword of my presentation today, and that is the dyn keyword, dynamic dispatch. That's essentially exactly the same code that you have seen before. The only difference here is that now I'm using here the dyn keyword. What I get from the dyn keyword is a so-called trait object. Technically, I get a kind of vtable, a table with virtual function pointers, and the method dispatching is done through the vtable. So in this case, again, I call print sound for two animals, cat and dog, but see it up here? It calls the print sound method in assembler language, and the print sound method in assembler language up here, I copied it out here. I don't have two print sound methods here. I just have one print sound method here. And this print sound method makes an indirect function call through the vtable. And of course that is slower, but I don't need a duplication of the methods here. I don't have monomorphizations. There are a lot of situations where you need this trait objects, and I cannot go into the details here because this is not a training, this is just a talk, and I limit myself to 1 hour. So I just can give you the facts, and you have to read up the details when you have to use trait objects and when you can use the impl keyword. The compiler will tell it to you. So if you try to use impl where it doesn't work, it will tell you use dyn. And if you use dyn and you use it in the wrong way, for instance, if you need to create a box and put the dyn in it, trust the Rust compiler. The Rust compiler will lead your way. You will love it, hopefully. Maybe you will hate it sometimes, but the Rust compiler is always right. It will guide your way. That's the beauty of the Rust compiler. Okay, that was a lot of content for 1 hour. But I wanted to give you an idea what traits really are, and that they are more than just interfaces. I think traits really rock. What are the most important things that you should take away? You should take away that traits are one of the underlying major concepts of the Rust programming language. Type conversion, operator overloading, iterators, everything is built on top of traits. You get zero cost abstractions through monomorphization, or if you don't need monomorphization, the traits, you don't have to pay for the traits at runtime. Yes, dispatching, dynamic dispatching is possible with the dyn keyword, but it's not a must. It depends on the situation and on your code. I hope you found this 1 hour interesting. I hope you enjoyed today's Rust Linz meetup. We are now pretty at the end of our Rust meetup. It's getting dark now. The video beamer now works perfectly fine. Before we go to the fridge and take a last drink and maybe talk a little bit, chat a little bit about what you've heard today, about your experiences, let me ask you, do we have any urgent questions that we should discuss before we get some additional drinks and eat the rest of the Ferris cake?